everyone, welcome back. This is the part 2 videos in which I'm simulating the solenoid in the Ansoft Maxwell software. The idea here is that we want to put a conduction path into the coil. And before I introduce the conduction path, we need to understand why it's needed. So when you have a geometry, you gotta create a region of influence around the geometry, and that will give you the numerical solution inside of that region. And the region is created by clicking here or by doing your own region with the draw box. But by clicking here, you create a region which will touch every single face of your geometry. And it's not touching the faces in which I want to put some excitation in the coil. You see, you need to put some excitation in the end and in the outside area of this face here and the one below. And that's what we want. But since the region is not touching there, and if you wanted to do the simulation here, we will have to put the region only in the coil, and we want to simulate all of the geometry here. We need to put a selection as a conduction path. So why should the region touch it, the excitation phase? Well, that's a requirement of the Maxwell magnetic solution type. Because in order for the software to understand that you are putting some excitation into a conductor, you need to have the excitation planar entity touching the region of influence. So in order to do that, we should create wires that are essentially what you have in real life. You create wires and in order to put a current into a conductor. Well, so let's do that. So we see here that we have the faces here on the upper part and in the down part as well, facing the other way. And now we want to create some wires, and the fastest way to do it is by drawing a line. You want to choose the right center of it. You see the right center of it, and then I want my wire to be facing in this open area here and facing outside of the material. And by clicking done, you finish the line. You see, that's what I had. I am not refining the lines. I'm just creating the idea of my directions here, and I will refine it later. And then I move forward to the other side here, the bottom part, and let's just put a little bit of a rotation here so we can see the center very well. And now let's choose the line again and do the same idea. Put here and there. We will change the dimensions and everything else right now. So now that we have the lines created both in the part below and the upper part, let's put some dimensions of it. My idea is, as a design idea, I want them to be facing in this direction here, and that's what I am creating right now. So basically, I want them to be parallel to the Y direction as well, and that's what I want. So let's do that. You see the lines are there here in my tree. I want to give them names. That will be easier to understand later when I'm creating the geometry. So the polyline number 1, which was the line I created in the upper part, would be called the conduction path up. Very well. And the one below is going to be called the conduction path down. Saves a lot of time to do that. I know it takes a bit of time to write it, but it saves a lot of time later. So let's move on. Now the idea is to give them some dimensions, and in order to refine the lines, you see they are not that they're facing like a direction I don't want here, and let's change that. So let's choose the conduction path up and create polyline, and here we see that this one is displayed now and the other one will be displayed when I click here. And let's check the first one here. So when you double click it, you see point 1 and point 2. Point 1 refers to the point in which the line starts, which will be the center of the geometry we choose. And the point 2 will be when it ends. What I want to do is I want to copy and then paste it right here, the same. And now what we have is that the line, this line here will be like starting and ending at the same point. We don't want that, but we want it to be at the same numbers, both in the X and Z axis. So what we want to do is only change the Y axis here. Let's change by a factor of 15. That's what we want. So let's see the difference. So you see that it's quite straightened up right now. Let's do the same with the second line. And we wanted to do the same idea here. But now we want the Y and the Z plane to be the same. The Z axis should be the same, but changing in the X axis. The X axis is facing to our left here, so we want it to go to our right according to my design idea. And in order to do that, let's just give it a number. Let's say 15. But I want it to face that direction, so I put it minus 15 because that's the minus x direction. Very good. So now we see that it's quite straightened up. That's what we want. So let's go to the other line. That is the conduction path below. And I'll just put the image there so you can see what I'm doing while I am choosing it as well. So here we have it. It's quite different from the upper one because we did it like just the lines. We didn't choose any kind of direction, but that's what we are going to do now. So the first line, it is starting at the 5 on the x-axis, and the other ones, they're all 0. We want to put in the y direction minus 50 here. Very well. If I'm not wrong, this is minus 10, right? Okay, very good. So this is what we have, and I want that to go inside there, just as the one on the top. So I will keep it the same in the y and z and change it in the x, minus 15 as well. And now we have both of the lines created, and let's see what we have here from the upper part. So we have the lines, they're coming out, you see they're going outside of the region here and going inside of the material zone we created here. Very good. That's what we want. So let's move forward by creating the wires in these lines. The idea here, you choose each one of them, but you gotta choose it separately. Create a polyline, and then you see type here, and you go to rectangular. Good. So now I'll put some width and some height in it. I'm choosing .5 and .5. Good. Now you see that the line is already a wire. It's a square shaped wire, but that's okay. It's going to simplify the problem. And also I don't want to check what's going with the wire. Just want to check what's going on with the solenoid. I'm going to do the same idea with the upper line. You see the connection path down already changed to a solid because now it is 3D. And now doing the same thing with the connection path that is in the upper part. Let's create it as a rectangle as well. And put it as 5, and as 5 here as well. .5, my bad. .5. Very good. Now that we have it done, we can see it as a better view from this view here. So we have the wires going in that direction. That would be good because that will separate what I want to simulate and where the excitation begins. And that will be where my regions will be touching in this place. So let's go to the region. But first of all, before we go to the region, I want to do some choosing here to the materials of my solution, so of my simulation. So let's choose the conduction path down, conduction path up, and the solenoid, and let's give them the same material. The material I am about to choose is copper. So let's go to copper. Very good. So we have copper here. They're all separated into copper now. So I want the outside box to be as a perfect conductor for now. Very good. So we have a perfect conductor selected. Very nice. So those are the materials I have. Let's have a better view now. Very good. So this is the geometry. And now what you want to do is to create a region in which will be the region of the simulation, where the numerical simulation will proceed. So let's create a region. The easiest way to do it is by clicking here and create a region. So let's do it as default. This will put no offset, so the region will be created in all of the geometry faces it finds, and that's what is happening. But you see here, what matters is that this place here is touching the wires. The other regions can be expanded into the direction you want. And that's what I'm going to do right now. So by clicking there again, I can have here the offsetting of each one of the axes. The minus axis on the x direction, I don't want to change because that's the one facing and touching the wires. So let's go to the upper, the axis in the plus direction here. I'll put it offset of 100%. That will duplicate the size on the plus x direction of the box that we already created. I will do the same thing with the plus on and with the other axis in both directions. But I'll put a 50 on these ones. Very good. So now that my region is created, we see that the face of the the region on the back part is touching the wires. Next thing that we should do is put some excitations in the wires. So let's do that. So we already have the wires here. Let's change to them. Let's go to them. And the excitations only works for planar entities. So you would have to choose only the face that is touching them in order to put the, the excitation. So let's go to the upper part of wire and put some excitation, current. I'll put it 120 amps, which is the amount of amperes that are required for my solution here. I want to choose the direction. I want this to be coming out of the wire, and the one in the on the bottom part, I want it to be going inside of the wire. You gotta be aware that if the wire is not closed, you gotta choose a direction that is current with what you want, which makes you gotta choose a current direction that makes sense. So it wouldn't make sense the direction to be both in the upper part and the down part to be facing on the same direction because they will be intersecting. So you want it to be continuously throughout the coil. Very good. This one is chosen. Let's go to the other one. I already chosen from here, but you could have zoned in as well. So let's go excitation, current, and put it 120 as well. You can see the arrow is already facing the direction we want. Very good. So now that we have the excitation done and we have the region done as well, we see that the face of the region is touching where the excitation face is assembled. That's what we want. And now let's proceed with the solution setup. In order to proceed with the solution setup, you just press it here, and I leave this as default. Okay, so now let's see if everything is okay by pressing validating. You should have an error of boundaries and excitations if you do not have chosen the excitations to be in the face of the wire in which is touching the region. That will be a main problem that happens a lot when you're trying to induce a current into a conductor. Good, so now that the validation check is complete, we can see that it's checking with a green arrow in all of them, which means that everything is okay, and then we can move forward. So let's move forward and do the meshing. Analyze all, and let's see the results. Very nice. So now that the analysis is complete, we can move forward and check the results. So here on the 3D design project manager tree, you just press plus, and then you have the field overlays. I want to check the flux field, magnetic flux field around the coil. So let's choose the geometry we want, which is the geometry of everything, and go to field overlays. Now let's go to see what the vectors are for the magnetic field. Let's see what we have. Very nice. So look at that. So we see that those arrows, they show the magnetic field, and you can see that inside of the solenoid, they go straight forward and up because that's the direction of the magnetic field when the current is going down to the upper part. And you know that by theory, if you have, let's say, in this plane here, the current going in the x direction and the velocity is the same plane as the current, you will have the magnetic field to be facing up. So that's what we have here. And that's good because it follows with the idea of the theoretical solution. That's really nice. Very nice. So let's move forward to seeing the magnitude and see the relation between the field created by the coil and the material surrounding it, in which in the case is a perfect conductor. The idea here is to do the same thing that we did by choosing the vectors. But I want to have the magnitude of the field being displayed in a plane in order to save data and also to have a better view. Let's do the same thing we did, but now choose the magnitude of it. Choose all objects again. Let's move forward. Now we see something. I'll put some animation in order for us to see it better. Let's check it out. So animate and the normalized distance, which is the z distance. I added some animation here, and as you can see, there's a field on all of the region. It's quite low though, but there is field. But inside of the perfect conductor, you have no field at all. You can actually see through it. And what's happening here is a really interesting magnetic effect that I'm going to introduce in another video. It's called Meissner effect. Thank you very much. See you next time.